IMT2531 så kan du faktiskt få en generaliserad VCE
All right, shall we start? Are you still motivated or bored or tired? Or
tired and mildly motivated.
why? Is it not clear? Is it like too easy, too difficult, or?
Well, I did say mildly motivated. I'm rarely extremely motivated for anything.
All right, let's continue then. I'll just make sure that it's streaming. Yeah, it should be streaming. Okay. Yeah, we have had a brief look how the pipeline works, but now let's have very brief introduction how to actually use this pipeline. Well, it's first of all a configuration machine. We have to configure, we have to provide inputs to make it work, and we have to first declare those inputs for some particular cases. Well, initialization of attributes, like which version of OpenGL is it using, which profile, whether it's a core profile or legacy profile, organizing the input, so actually creating vertex array objects that describes the organization of our data, our model, instantiation of input buffer, so creating vertex buffer object, the actual data, actual coordinates that defines whatever we have to render, and then filling it into buffer and activating it. And the next step is to plug in the shader to activate the shader to feed this buffer object that we have defined into the shader, and to make it use an assign or whatever manipulation we have programmed and defined in the shader ourselves. At least vertex shader to make all transformations right, and it operates together with rasterization step on the GPU. And to make actual execution of displaying them on the screen, we use these GL draw arrays, and when we don't use the buffer, we then deactivate it. And to swap whatever we discussed a few minutes ago, like from a back buffer to the front buffer, we also have to do that ourselves manually, and I mentioned that this gives us opportunity to control the frame rate and to control whatever and when it is displayed. Yeah, in this case, this function is SDL implementation, but if you are using other solutions, like you have to find corresponding function in GLFW or whatever to swap them, it depends on whatever windowing you are using for your solution, but this is just example from SDL GL swap window function. So first we need to define vertex array objects, and this doesn't know anything about particular vertices. It doesn't know whether it's in 0.05 or whether it's here or whatever its values are, but it knows the semantics, how the data is arranged and how it should be interpreted and understood from the vertex buffer object. Here are two functions. If you have your laptops here, you can open maybe the first lab, and actually those codes are primarily from the first lab, so you can maybe, as it looked like a black box, then maybe you can start understanding it slowly what's happening there. So if you want to open your code from the first lab, you can feel free to do so. So we have two functions. Well, first of all, OpenGL functions are very easy to identify and recognize in the code. They start with GL, and so are the data types. GL generate vertex arrays as it's very intuitive and logical to generate vertex arrays. We have one integer parameter defining how many vertex arrays we want to define, and the second one is a pointer to the location of the identifier array ID. We will see here on this slide. The second function is just binding function that to make it simple is activation or opening this object. So here have a look on the bottom part of the slide. So the GL unsigned integer data type vertex array ID, we just define the ID, and when we are generating a vertex array, we actually pass as a parameter pointer to the location where its ID should be written. So it's our responsibility to allocate a space for this array identifier. And usually in the literature you can see cases where like you can create I'm sorry, where you can create like several arrays at a time, but this might lead to crashes, like if you don't allocate enough space, enough elements in the array for array identifiers. For example, if you have like 3 element array for identifiers and you're trying to create 5 vertex arrays, it might lead to crash or like you will have problems with actually processing glitch code. So the rule of thumb is to create vertex arrays one by one, just like here. Define identifier and create one vertex array object, and then if you want the second one, and so on. And afterwards we have to bind that, where we use GL bind vertex array function and just pass this vertex array unsigned integer identifier as a parameter. So this binding might at first look very strange or unnatural if you are not familiar with this. It's actually like I made a comparison like having a docx object and the content in it. So let's imagine that the content, whatever is written, is a vertex buffer object, and the vertex array object is a program, but you need to open it. So you have it created, you have it in your system, but you need to open it, and you need to attach to the shader to make it readable and functional. So binding is just like, to make it simple, activating it, making it ready to use. And usually you don't need to unbind it. So when you bind another one, it will automatically switch to that. Actually, the process is identical for vertex buffer objects, where we have actual data. It's a very similar process. We have first defined ID, unsigned integer, and then we allocate buffer on the GPU, and then we generate buffer GL GAN buffers. We generate one of the buffer objects, and we pass a pointer to this identification space, so the space where identifier is stored, and then we bind it. And this parameter GL array buffer just defines its OpenGL parameter and defines what kind of buffer we have, because we might have other types of buffers like color buffers or texture buffers or whatever information we need in the process of rendering. But in this particular case we define that it's array buffer, and we again pass the identification. As I mentioned, like we can just change what is bound instead of unbinding and binding a new buffer. Actually, to make it more clear, whatever we have here, that let's imagine this is a pipeline. And here we have shader that should execute the program written by us. For example, let's say it's fragment shader and it has to assign the colors. And we have several buffer objects. So when we bind it, we actually bind it with the shader so that the shader can use this information for processing. When we want to switch to this buffer, we don't need to unbind it here. When we bind this one, where there is a new bind, this is automatically unbound. And we start now processing this buffer using the shader, and that so on. So that's why even if we define it in the code, it's important to bind it to make it usable. Now we have created a buffer object, but we need to actually fill it with actual data. So mostly, in most cases, this is just simply by reading from an external file. But let's have a look how it's done, like manually by actual definition of the content. So yeah, here is a function GL buffer data, and we have target defining what kind of array we have. We have buffer array in the array buffer in this case. What kind of buffer we have? Yeah, array buffer. Then what is the size of the content we are gonna fill in bytes? How many bytes does that data we have to write into? How many bytes are we going to write in? Then the actual data, and then the usage, whether it's static or dynamic. So I will explain this. So here we have a floating point array of 9 elements, and as you can see, like those are some numbers. And we have like x coordinate, y coordinate, z coordinate, x, y, z, x, y, z. So we want to define 3 points using this. That's actually what we want to have. Define 3 points, 3 vertices in space using those 9 coordinates. We call GL buffer data function. We indicate that it's an array buffer. We pass size of overall data in bytes, so it can be simply done by size of this array, or if you want to calculate, you can, like here we have floating points. Each floating point variable is 4 bytes, and you can just calculate by 4 number of elements by 4, and you can put that number here. Then we pass vertices, this array that actually includes the numbers we want to have as a coordinates, and then we define it as static, so we do not expect this to change. So if we define it as a dynamic, this means that we ask the machine to check it on several iterations, because it's updated from time to time. But in this case, we don't expect to have any updates. We want these fixed coordinates. Okay, we have created this buffer data, but how this should be interpreted, how machine can understand that, okay, we want this to be x, y, the third element to be z, the fourth element to be x, 5 to be z of the second vertex. So how should we make this clear? Here we need to use GL vertex attribute pointer function. And if you have a look in your lab, it's very easy to understand what it was doing that time when you did the lab 2 weeks ago. So what are the parameters here? The first parameter is identifier of this attribute pointer. So this is the unique number the shader uses to refer to this data and interpret it this way. So it is extremely important to pass the right number to the shader to make it understood as we want it to be. And this can be any number between 0 and 16. The maximum number can be 16, so you can assign any number as an identifier to these particular attributes. The second parameter is just size of components per vertex. So in this case we have 3 coordinates, x, y, z coordinates. So we say that we have 3 elements per vertex. If we had 2D, we could write 2 and it would understand like x, y, x, y, x, y instead of x, y, z. Then we just tell it what is a data type. We have floating point. This parameter means whether we want to normalize our values within some range. If we want to have our numbers normalized within some particular range, but usually in most cases we put this one to false. And stride is just spacing between vertices, so these triplets of coordinates, how many coordinates are in between them. I'll explain this shortly. So an offset is simply where we want to start. In this case we want to start from the very first coordinate, so we start from here. If we wanted to start creating vertices from this coordinate on, we could write 4 instead, not 3. Yeah, what is stride? Imagine that we had texture information as well here. So in this case we have x, y, z, but imagine if we had x, y, z, u, v as texture, or to make it simple, color maybe, x, y, z, RGB, x, y, z, RGB, etc. So we have 6 numbers, 6 elements of this array assigned to one particular vertex. But the machine doesn't know that. If we want to use color and vertex coordinates, we can write stride 6. So it will be 6 objects for one vertex, the next 6 objects for another vertex. But what if we just need to use coordinates, special coordinates, and just don't care for color for this particular case? How should we tell that to the machine? We write here that stride is 3. Sorry, it's in bytes. So stride is 12. We skip 12 bytes, so 3 elements. So what it will do is that it will start x, y, z. Those are color information, so it will skip this one, and this one, and then it will continue x, y, z, and so on. So this means how many bytes we want to skip from one vertex to another. It means how many bytes are allocated for other things other than what we are interested in. If we are interested in both color and space, then it's 0 because all the data are needed. Is this clear? Okay, let's have it here and maybe on this side. Maybe smaller. So we have x, y, z, r, g, b, x, y, z, r, g, b, x, y, z, r, g, b. So this is what is in our array. And now we have these numbers written in the array, but we want to use, so this is one vertex, like let's say this is another vertex and this is another vertex. So 1, 2, 3. So this is clear, right? We want to define 3 vertices and we have 6 elements, x, y, z, RGB, x, y, z, RGB, and so on. Now we want to pass just the coordinates to the shader and we don't care for color in this particular case. How should machine know which elements should it read? We should indicate that, okay, after reading 3 elements for this particular vertex, skip so many bytes to start reading the next vertex. So if we write here 4 bytes, 4 bytes, and 4 bytes, like this means that it will read like x, y, z for first vertex, then it will skip 12 bytes. It will start reading again x, y, z. It will skip 12 bytes. It will start x, y, z. If we want to have color included, then the stride is 0. So it will read x, y, z, RGB. Doesn't skip anything. It will start x, y, z, RGB. If we set, for example, stride to 24, what it will do? We read this x, y, z, RGB. We skip this one completely, and then we have this one, right? So this is actually how many bytes do we skip after we start reading the information for the second vertex. Okay, let's check whether, yeah, this is location identifier in shaders. So actually the ID, whether how shader identifies these attributes. Okay, this is more interesting now. So we have XYZ data, vertex data, and we have texture data, UV, and they're like interleaved, means like put in this way. So imagine here is UV, UV, etc. So each floating point is 4 bytes data. So what should be the stride to read just the coordinates and not the texture?
Just the coordinates and no texture?
Yes.
0?
No, if you have 0, you don't skip anything. You just read, like, you read XYZ UV, XYZ UV, and so on.
Oh, 8 then?
Yeah. Yes, because you skip U and V, and U is 4 bytes and V is 4 bytes. So is this clear for everyone? Yes?
So if you have the RGB values in addition, then your vertex has a size of 6. But in the attribute pointer that you just showed, it says the maximum size is 1 to 4.
Components. Size of
Number of
components
per vertex 1 to 4.
Oh, this is, I think, just the coordinates that can be X, Y, Z, W.
Okay.
That, Christopher?
In this example?
In this example, the comment says 1 to 4, the size, but actually we can have more, like we can have XYZ UV, right? Like in this example, interleaved together.
Yeah.
So this 1 to 4 refers to the coordinates only, I think.
Yeah, that comment, dismiss that comment there.
Yeah, I think it's XYZW. That's how I understand that.
XYZ W. Yeah. So, but yeah, you're flexible, right? So you can use it arbitrarily, right? So it's just.
Yeah, you can have 5 for texture
right.
UV,
That's
or you
right.
can have 6 RGB.
Right. You can pretty much encode anything in there anyway. It doesn't mean you use it, right? So it's just data, right? If you want to use it for other purposes, that's entirely flexible, right? Halvor, any take on that?
You said it all.
Huh?
You said it all.
Yeah, right. So it's like super flexible, right? So it's in fact, just think about a data structure that you feed now and that you link somehow for usage, but fundamentally you can also just load stuff you actually don't use in your graphics. I mean, it's just a data structure. I think that's an important thing to bear in mind. So the 1 to 4, ignore that. That's probably need to clear that up a bit.
Yeah, maybe I should remove that because
Yeah.
it's confusing. Yeah, here is very nice representation.
So you have
Like
X, Y, Z, and then texture
Each
coordinates.
floating point is 4 bytes. So if we want to read just XYZ, like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and we want to skip texture, we are not interested in. We want to start reading XYZ of another vertex. So if we set stride to 8, we say to to the machine that, okay, skip those 8 bytes. If we didn't do that, then it would read those ones as X and Y's of the second vertex. Yep.
If we set the stride to 8 and we skip the colors, when will we read that information later? Will that be like in the shaders that will get the color data, or?
Then you have, I think you have to define a new
information.
attribute pointer with new index, and you will refer to that from the shader.
Yeah, but then there's some color information that we're gonna have to read later.
Yeah, then you have to define this one, another one like this with a new index with different stride, and you will pass this number to the shader.
And you could have two of those vertex attribute pointers running over the same data structure, right? Just picking different stuff, right? So it gives you the entire flexibility and decouples a bit the generation of the visual output from the data structure. So you can, you know, twist. You can have multiple buffers anyway, right? So that you can consume from, or a single one that keeps the entire complexity in there, right? So just to keep that separation clear, you don't need to exploit and comprehensively use one buffer. It's just a matter of you organizing your data. You will see an experience and play with this, I believe, around as well. Once you actually start writing your own tools, you can see if it makes sense to actually have multiple buffers or only one and multiple pointers. Yeah. So I think there's no hard and fast rule. It's probably pretty much down to what you want to do. Yep.
So from what I understand, it's basically do the interleaved stuff. It's sort of when you're accessing it, that is, and how often it changes, that you're supposed to base that on. So you don't
yeah,
really
that's the engineering decision fundamentally, yeah. Right? So when to use multiple and so on. But here at this stage, it's just about to get across. Okay, you're very flexible in your the data structure, and the only thing you need to be specific about is actually, well, because this vertex attribute pointer links basically to what you will render ultimately in this iteration of the code, right? How it's then unlinked to the underlying data is specified there, but it may just change in the next frame, basically, right? So,
yeah. So this is the data structure we defined, but this attribute pointer, so the instruction how to pick this data can change from frame to frame. Yeah, and activation of those buffers I'm putting into drawing. Like, if we have a look, we need to enable vertex attribute array, and what you see, the 0 here is actually this 0. So we pass this index, so instruction of picking the data, it has its unique identifier, we pass that to this function. And on the next line, we just call GL draw arrays function, and we put what kind of primitives we would like to use. We want to use triangles, we want to draw triangles, and we start drawing triangles from the very first vertex. So this one, oh, sorry. So in this case, we start from this one, and this one. So this is the first vertex of the triangle. This is the second vertex. This is the third vertex. And we just tell them to have the 3 vertices in total. If we want to draw like 5 triangles, we can write like starting from the same 0 and having 15 in total if we want to have separate ones, or we can have different ones. We will see geometric primitives because the same vertex can be used several times in several different triangles. And then, yeah, when we enable the usage of this one, then we deactivate this input buffer, and then we, using this SDL function, swap the buffers to visualize. So, yeah, primitives. What are OpenGL primitives? It can be points, it can be lines. So the lines means line connecting 2 separate vertices. We will see this on the next slide. It can be line strip, so one kind of long line of different segments. So the first vertex is connected with the second one, second is connected with the third one is connected with the fifth one, and so on. I think it's easier to understand this way. So those are points. those are the lines. This is a line strip. Line loop is a closed line, so when we just connect the last one and the first one, it's a line loop when we make this line and just connect first and last one to close it. Well, we can have triangles, or we can have triangle strip or triangle fan. So what's the difference between them? Triangles are just separate triangles defined by 3 unique vertices, while triangle strip is that every next triangle is using 2 vertices from the previous one. So we first drew this one, then the next one uses vertex 4 and vertex 5 and adds vertex 3 and defines a new one. Then the next triangle uses vertex 3 and vertex 4 and connects with vertex 2 to define the next one, and so on. Then vertex 3, vertex 2 are used for this triangle, and so on. And triangle fan is when we have just one point participating in many different triangles, where in this structure, as you see, like the new triangle uses 2 vertices from the previous one, but one vertex remains always the same. So we have one fixed vertex used in all triangles. We define first triangle, we add a new point using those 2 vertices, we add another point using those 2 vertices, and it's finally as a fan. It has a shape of the fan. Except for that, we can have polygon defined of any arbitrary number of vertices having any shape. This is very nice shape in this case, but it can be very complicated shape too. We have, as you have mentioned in the beginning, quads or quad strip that is actually identical logic as triangle strip. So every next quad is using 2 vertices from the previous one. And finally, a few words about game loop, how this is put in actual gaming and in the loop. So we activate the input buffer to be rendered. We draw that using, so it's actually this process, activate buffer. We defined buffers here, we filled the, so we defined buffers, we filled with the data, and we feed this to actual pipeline, right? Then we activate the buffer, draw it using this function, we deactivate it, swap buffer from the back to for the foreground, and you might have some modification after illustrating, after displaying one buffer, like we might there might be a motion, animation, perspective change, or anything in the game. So we change these vertices, we change the locations, and then we feed that data again to the activation. So we start from the very beginning and so on. And this is how we have this seamless movement in the game. So taking coordinates, activating the buffer, drawing, deactivating the buffer, swapping to display, then changing the data in the buffer of the object. For example, if the car moved from point A to point B, and then start the same process again. And this is an infinite loop that makes the game run. So until we have some external command to stop, this is run infinitely to make the game run. Yeah, those are the major points, I think, for today. Next lecture will be very important. We will actually start discussing vertex shader and fragment shaders, and we actually start working with transformation, manipulating with the shaders, going more into deeper details. And yeah, looking forward to seeing you on that lecture. For today, yeah, if you have any question, if anything is not clear, please feel free to.
Just one brief disclaimer, just for the sake of the slides. If you go back, yeah, so that is all good. If you go back one more, Yeah, there. So for the ones that actually want to retrace the code from the first lab and actually just want to see those patterns there, the only function is different. It's the last one. Here's called SDLGL swap window. The reason is that this was written, as mentioned earlier, using helper tools, right? Like SCL and GLFW.
Yeah.
To do window handling. And those tools, those functions are different, right? They're specific to tools. This is a demo code for SDL. And the one we are using is of course slightly different. So you will see something that's called GLFW swap buffers, I believe. Is that right? GLFW swap buffers. So if you see that, that's the same thing. Doesn't matter. Just for this, for the framework we're using. The rest is identical, however, right? So just so if you stumble across that and you're slightly confused, that's the reason why. Nothing relevant. You notice anyway that started with an SDL, so it's specific to the fact that it's actually describing a different framework, which is not OpenGL per se. It's just this window handling mechanism. Whereas all the GL cores are of course native to OpenGL cores, right? So.
Oh, just
yeah.
one thing. You started the class by mentioning that you wasn't going to publish the first assignment yet. Does that mean that the deadline is extended, or the assignment?
Yes, of course. Yeah.
Is there a deadline already?
I'm not sure.
So then,
no.
how would you know that?
Yeah.
Let's just say yes.
I thought we got a deadline, but I'm not sure.
I will check that, but logically, yes. If the announcement is postponed, deadline will be also extended proportionally. Definitely, yes.
Yeah.
No worry about that.
I
no
don't
worries.
think, so the point about the assignment will be, of course, it only makes sense to provide it when we actually have. When you have sufficient background, right? We had the experience if we gave out assignment too early, that people would get crazy and copy all wild stuff from the internet just to get stuff done because they feel, oh damn, I'm behind, I don't know graphics. And surprise, surprise, we didn't teach you anything about graphics yet. And that's very true. I mean, that's effectively the first session on graphics itself. So it's little point giving you the assignment too early. We'll give it to you timely, and by experience, it's more than enough time to finish the assignment. But you need to start kind of, to be on it, because graphics is graphics. It's like it's hard to plan if you don't know it yet, right? So, did we have enough time last year?
For the first one, yeah.
Yeah, right.
Well, it was stressful, but I think most got it.
Just ignore the details right now. It's feasible. That's the main thing. So, yeah, well, it's stressful because it's a different mode of thinking, right? So it's not much code you'll write, probably, terribly much, but it's really about that you need to experience a bit of a twist in thinking, because how OpenGL works slightly different from what you're used to, and that will accommodating this will take some time, right? So, but don't worry about the deadlines. We'll deal with this, and there will be enough for the average student workload to deal with this. So, yeah.
And even if we see that you need really time for working on your assignment, we might kind of skip some lectures and have additional labs to give you opportunity to work and practice coding. So it's very flexible in that terms. So we will see what kind of workload you prefer in that sense.
Yeah.
And yeah, if you have any questions on today's lecture, feel free to ask. Because I had impressions that this part was not very clear to everybody. So is it now clear what this stride parameter does? Does everyone understand that? Great. See you tomorrow then. And thank you for your attention.
May I ask you one quick question? What possible reason could you have to include John Kennedy reloaded in the official slide? Why not? I don't know, but it sounds like